This presentation is about zero-field nuclear magnetic resonance, or NMR. NMR is broadly used for structure determination, with hydrogen-1 and carbon-13 NMR being the most often used by organic chemists, as hydrogen and carbon are the primary constituents of most organic compounds. A nucleus with an odd number of protons and/or neutrons possesses a quantum mechanical property called nuclear spin, and can therefore be probed by an NMR spectrometer. This is an image of a 300 MHz NMR spectrometer, similar to the one in Doble Hall at UNCW. The spinning proton/neutron or protons/neutrons generate a magnetic field called a magnetic moment. In traditional NMR, the magnetic moment is subjected to an external magnetic field, the strength of this magnet varying. The spinning proton/neutron either occupies the alpha spin state, aligned with the external magnetic field, or the beta spin state, aligned against the external magnetic field. Conventional NMR is high-field NMR, where the field refers to the magnetic field the instrument generates. There is high field, medium field, low field, and many more in-betweens before reaching zero-field NMR. So what is happening to the sample inside the instrument? There are three main stages: polarization, encoding, and detection. I want to go over these stages as zero-field NMR has the same stages, but they occur in separate spatial stages and occur differently, so we can compare and contrast the two instruments and how they function. The nuclear spins of the sample are thermally polarized in a superconducting magnet. Then, information about the molecular structure of those samples is encoded from the spin resonance frequencies, and these frequencies depend on the applied magnetic fields and the internal spin-spin interactions. The detection is traditionally with Faraday induction coils. In zero-field NMR, the magnetic moment generated by the spinning atoms are not subjected to a magnetic field, and zero-field NMR spectrometers are designed to even eliminate Earth's magnetic field. Shown here is a diagram of the inside of a zero-field NMR spectrometer. So what's happening inside the instrument? There are the same three main stages: polarization, encoding, and detection, and they are a bit different than high field. Zero-field NMR uses permanent magnet arrays to polarize nuclear spin samples. These magnets are weaker than the superconducting magnets of the high-field NMR, but they are low-cost and portable. We can see the magnet in the diagram here. The encoding to spin resonance frequencies is done through internal spin-spin interactions, such as J-coupling and dipole-dipole interactions. In high-field NMR, the spins are coupled more to the magnetic field than to each other, but in zero-field NMR, the spins are strongly coupled to each other by these spin-spin interactions. Detection for zero-field NMR doesn't use Faraday induction coils because of the low frequency it operates at, and the Faraday coils aren't as sensitive as needed. Thus, zero-field uses non-inductive sensors. One limitation of zero-field NMR is individual manipulation of different spin species are more challenging than others, and this limits the uses of zero-field NMR. Thus far limited to homonuclear spin systems, where the spin-spin interactions are between the same nuclear spins. Heteronuclear describes the spin-spin interactions between different nuclear spins in a molecule. Resonance frequencies are not as well separated in zero-field NMR, and the selection of individual spin species is not as straightforward and presents a challenge while limiting its applications. Though there are some quantum control methods that have been and are being developed to overcome this and other difficulties. Over all of this, the main disadvantage is low sensitivity. There is negligible spin magnetization, Therefore, an external source of spin polarization is needed. Zero-field NMR can be cheaper than high-field NMR, as superconducting magnets are expensive, in the region of $1 million. They require constant cryogenic maintenance and are immobile, though there are less powerful benchtop NMRs that have been coming out recently that are more mobile. The NMR pictured before and now is certainly immobile, and if anyone here used the Doble Hall 300 MHz NMR, they would know that every week it felt like it was down for maintenance and it was incredibly tedious. Without the need for superconducting magnets, zero-field NMR spectrometers can be inexpensive and portable in comparison. Here we have the zero field on the left and the high field on the right. And right away, we can see that the zero field is a lot smaller. The sample tube in both images are the same size, showing exactly how much more portable the zero field NMR spectrometer is. Some disadvantages of the strong magnets used in high field NMR are that it has the inability to observe signals through conductive material, except for a few special cases, and the significant spectral broadening in heterogeneous materials, both of which are solved by using the zero-field NMR over high-field NMR. Additionally, zero-field NMR can measure spin-dependent interactions that can't generally be measured with high-field NMR, and the direct detection of spin-spin coupling allows for probing the collective effect of exchange upon two or more nuclear spins, rather than just probing a single nucleus as in high-field NMR. The image here helps visualize some spin-spin interactions between nuclei and protons in either spin-up or spin-down positions, with various ways they can be spinning and the energy of those spins. A new way we can tackle MRI instruments in hospitals is by using zero-field NMR. MRI and NMR are the same instrument, and so using zero field can make MRIs accessible to people who may need the imaging but can't access the healthcare that they need. Some patients have pacemakers or metal joints or metal plating, and as an MRI is a large magnet, they can't use it. MRIs face some of the difficulties of high-field NMR in that the instrument is expensive and immobile. One difficulty of using zero field for MRIs is the image quality improves with magnetic strength, so using zero field would result in bad imaging. Today, it is more likely to create MRI instruments that are technically ultra-low field NMR and not truly zero field, though research and experiments are ongoing. Right here, we see two MRIs using ultra-low field NMR. This one being an MRI of a brain, and this one being two fingers. And this shows exactly how imprecise and fuzzy the quality of the images becomes when we don't have a lot of magnetic strength. And I bet if it didn't say brain MRI or two fingers MRI, you wouldn't know what that picture was. This is a hard field to do research in, as any study involving humans has more red tape than using zero field to look at chemicals. But this is an interesting and exciting application that could possibly lead to more advancements in the medical field as well as the analytical technique. Zero-field NMR has also recently been used to study small biological molecules, like versions of glycine, fumarate, formic acid, and D-glucose. In this experiment, the researchers constructed a portable zero-field NMR spectrometer as well as an ultra-low-field NMR spectrometer using a commercially available magnometer, then used it to observe J spectra of small biomolecules. This experiment shows how easy it is to construct a zero-field NMR spectrometer, and that it can be used to measure spectra of coupling that high-field NMR would struggle with. The image shown here is a figure from the paper showing the zero-field NMR spectra of the various molecules the researchers studied. Another application of zero-field NMR is coupling it with hyperpolarization techniques. Hyperpolarization are experimental techniques that yield nuclear spin polarization levels several orders of magnitude higher than thermal equilibrium, resulting in enhanced NMR signals. This is a figure from the paper that uses this technique comparing zero field to ultra-low field NMR with and without hyperpolarization. We can see that there is a clear difference in the clarity of the signals. To summarize, zero-field NMR has its drawbacks, but it also solves some of the problems and struggles that we have with high-field NMR, as well as being less expensive and more portable. There are numerous ways to apply zero-field NMR that can either achieve better performance than high-field NMR, or in ways that high-field NMR can simply not be used. This application has grown leaps and bounds over the last decade, and there are so many more things that we can do with it even still. This is the list of references I used. I look forward to answering any questions.